So now we say a little bit more about this Arctic methane, which is a real threat to the continued existence of the human race. Given that there's a possibility that all of the methane from the Arctic will come out in a very short time because of melting of the sediments, what would happen? And well, I did some work with a computer model with colleagues, and we just modeled what would happen if 50 gigatons, that's 50 billion tons of methane, came out of the seabed in one go. That's only about 8% of the methane that's there. So it's the real disaster, the actual disaster that would happen could well be much worse than this. But if you assume just 50 gigatons and then model what that would do to the temperature of the planet, this is what we get. The blue, this is a family of curves which represent warming of the planet with different sort of assumptions about how good we are at taking greenhouse gases out of the atmosphere. So let's consider the blue, the middle blue here. This is the way the planet would warm up if we made some attempt to take carbon dioxide out of the atmosphere, but not a good attempt. This is quite likely to be what happens. But if you have this methane outbreak, it warms everything up. And here we have the red curve instead, is what happens to the planet with this methane outbreak. Now, in our model, the rise was only 0.6 of a degree. Now that's, given that the temperature rise has only been 1.2 degrees since the Industrial Revolution, we're getting a rise of half as much just immediately from the seabed methane melt. And even worse, our results were repeated. The work was repeated by an American scientist last year, and she got an even larger rise. She got a rise of 1.2 degrees using more recent modelling techniques. So the rise of temperature could mean that we're doubling the amount of warming from the Industrial Revolution simply due to Arctic methane coming out of the seabed, which is really a frightening prospect. Now, what would that cost? One of my colleagues is an economist and worked out what that would cost, and it would be something like $60 trillion in 100 years. That's the cost to the world of having all this extra global warming. $60 trillion sounds a lot, but it's only about 15% of the amount of cost that the world is incurring from emission of carbon dioxide anyway, but it's a lot. Now, methane is a cause of concern because of this thing I showed where the level of methane in the atmosphere seemed to be flattening off and reaching some standard level for some reason we didn't understand. But then it started to take off again, and now it's going up very fast. And we need to try to understand why that is. So what are the things that are causing methane to increase? We know what causes carbon dioxide to increase. It's burning coal, burning oil, driving your car around with petrol. Anything that burns fossil fuel, oil or coal, releases carbon dioxide, and that's causing the carbon dioxide rise and the global warming rise. That's simple, but methane is coming up fast, the amount of methane in the atmosphere, and it has a variety of sources. There isn't one simple source, just lots of them. And some of them are due to man, and some of them are due to nature alone. So these are some of the ones that are due to man. First of all, we produce far more waste than we used to when we had a lower population, and the waste is put in great piles, waste heaps, and decomposes, and as it decomposes, it releases methane. So that's waste sites. There's still methane released from fossil fuels. Especially gas. Natural gas is one of the main sources of heat and fuel for Europe. Natural gas coming from Russia, and that natural gas leaks as it's transported through pipelines and through various systems to burn it. It leaks, and the methane loss from leakage is large. Rice cultivation, a surprise. You think, well, there's nothing more ecologically viable than growing rice because it's the staple food in Southeast Asia. But the trouble is, you grow rice in rice paddies where it's flooded, and that flooding causes the rice leaves of the rice to rot, and that produces methane. So there's a source of methane, which is rice cultivation. And again, with the population rising everywhere, the amount of rice that people are eating is increasing. So the rice methane source is getting bigger. Domestic ruminants, these are the worst of all, and only recently have people begun to realise just what a bad effect cattle and pigs have on the world, especially cattle. The number of cattle in the world has increased really fast because in poor countries like China, people couldn't afford to eat meat, but now they can, and because they can, they do. And all of the poor countries of Southeast Asia, where meat consumption was low, the meat consumption has now become high, and that means more cattle. And cattle produce methane, enormously large amounts of methane, from the fact that the grass that they eat, they have to chew and redigest. And as they do that, and it rots inside their stomachs, it produces methane. So cows are big sources of methane, really serious sources, and that's quite a large chunk of the world's methane production comes from cows. And this is burning of biomass and fuels. So we see there's a variety of sources, and it's going to be hard to get rid of any of them. For instance, we can be more careful about getting rid of waste. We can't do much about rice cultivation. Cows, the hope is that you can feed cows with something different. Apparently seaweed is very good. If you feed a cow with seaweed, it doesn't produce as much gas. So we can shrink the methane, but it's difficult to do so because there are so many sources. Now, these are the natural sources, and the biggest natural source here are wetlands. That is marshes, water, rivers. It's where there's land which is wet and where the contents rot away. And whenever vegetation rots, it produces methane. So the biggest source are wetlands. But we see an increasing slice here coming from permafrost, because permafrost is the permanently frozen ground that you get in the Arctic. Now, the trouble is, permanently frozen isn't permanent anymore because of global warming. So a lot of the permafrost in the Arctic is melting and turning into water, but the water has got vegetation in it, rotting vegetation from the distant past, and that continues to rot and produce methane. So permafrost as a source of methane is going to become bigger and bigger source. Then some other ones here, termites generate methane when they're busy as termites. Fires generate methane, and wild animals do the same thing as cows, and fresh water is a source of methane. So there's a lot of natural sources, but the biggest natural source is wetland. So permafrost, while we're talking about permafrost, we should worry about it because permafrost is found under about half of Asian continent, most of Russia and some of China. And it's warming up because the climate's warming. These are some measurements made at a place in northern Alaska called Dead Horse, which is a very small town, has a population of 1. And I've been there. And every day, this one person measures the temperature of the permafrost at Dead Horse, and it's been rising, as we can see, quite rapidly. And everywhere you look, permafrost is warming up, and in some places is thawing out, turning into water with rotting vegetation, which will produce more methane. So methane in the future is going to be coming from the loss of permafrost. It's been called the ticking Arctic time bomb because it will take several decades for it all to disappear. So we've talked about sea level rise as one consequence of climate warming from the melting of the Greenland and Antarctic ice cap. We've talked about this potential huge methane release from the Arctic seafloor, which could be a real shock to the planet. So then the third thing I'm going to talk about is the jet stream and extreme weather events. Now this is another very serious problem which has occurred and which again has just been recognised. Now in the past, the left-hand picture here shows that there used to be a very steady, very strong wind that blows from west to east at some middle latitude of the northern hemisphere. That's the blue arrows. North of it, right under the pole, you have very cold air, polar air, and this is called the polar air mass. And then further south, near the tropics and the equator, you have a warm air mass, the tropical air mass. So you have a tropical air mass in low latitudes, a polar air mass under the poles, and dividing those two, you had a very strong eastward flowing wind called the jet stream. And you would know about this if you fly between America and Europe, because it makes you get from America to Europe more quickly than you get from Europe to America, because the wind is blowing eastward. So that's the way it was, and it was a very strong, very steady wind. Now what's happening now is that wind has slowed down. And the reason it's slowed down is that it's driven by the temperature difference between the Arctic air and the tropical air. And that temperature difference is decreasing because, as we showed, the Arctic is warming 3 times as fast as lower latitudes. So that dark blue cap on the planet of cold air, that cold air is warming up, and it's warming faster than the warm air in the tropics. The temperature difference between the polar and the tropical air mass is decreasing. And that decreasing temperature difference doesn't drive the jet stream as rapidly. So the jet stream is slowing down. And when it slows down, it stops being a steady, strong eastward wind and starts to become a wind that's broken up into little eddies or big eddies, and we see something like we see on the right-hand side, where instead of a straight line marking the wind is broken up and into eddies. And this means that in some places we find the warm air from the tropics can move further north than it should do because of a lobe of this jet stream that's tilted this way. And in some places, the very cold air from the polar regions can move further south than it ought to. So we have cold air occurring in places where it's normally warm, and warm air occurring in places where it's normally cold. So what you experience when you're on the Earth's surface is a sudden, extremely cold outbreak, something colder than you've ever known, or an extremely hot outbreak, hotter than you've ever known. So all the heat records are broken by these warm polar air moving north, warm tropical air moving north, and cold records are broken by the polar air moving south. Now, here we see a simulation of this by NASA, and here's the jet stream. And here we see it's taken up a shape where hot air from the Midwest, the midwestern states of the US, has moved further north than it should be. So you're getting hot air over the Canadian prairies. And over here, the cold air that should lie over the pole is moving further south and has got down to here, which is the eastern part of the United States. So the eastern part of the United States that's normally quite warm can become suddenly very cold, and the Midwest of Canada, which is normally cold, can become suddenly warm. These are the kinds of things that can now happen, and they're called extreme weather events. They're not climate, they're weather. So what happens? Well, I won't show you pictures of all the terrible floods and hurricanes that have happened, but you've seen those on the news. But what I can show you is what it's done to crops. Now, the brown colour here is the intensity in which we grow crops for food. And we can see that the food crops of the world are grown most intensely in the Midwest of Canada and the prairies, in Europe, in Ukraine, and in Western Russia. There's also India and China, but let's look at these places. These are the places where the jet stream has started to break up. So instead of reliable eastward flowing winds over these parts of the world, you're getting the jet stream breaking up into eddies and giving us unreliable weather. So when we need reliable weather for growing our crops, we're not getting it anymore over this very wide swath of North America, Europe, and Russia. And that's a real worry, because we know that most of the crops that people eat have reduced yields if the temperature gets very high. Now, these are the 5 main food crops grown on the planet, and that's maize, soybean, rice, wheat, and another type of maize. Now, in each case, if you warm the climate, this is the climate, the temperature as it was in pre-industrial times, as you warm the climate for a little while till the temperature's risen about 1 or 1.5 degrees, the yield of the crop increases. You're getting, if you warm the climate, you get more growth. But then when the temperature gets higher still, up to 2 degrees or more, the yield of the crop starts to go down very rapidly, and that's because it's withering away. It's drying up in the hotter climate, withering away, and you're getting less of your crop. So this is one of the main reasons why in the Paris Climate Agreement, the world agreed to try and keep global warming to less than 1.5 degrees. It's to keep it below a temperature at which crops have lower yield, and so we have less to eat. And we can see that we're getting up to that temperature now. And because of these weather extreme events, we've lost crops due to these sudden warmings and sudden coolings. And the extent to which this happens was calculated by the United Nations. The United Nations Climate Programme designed a measurement which is the average price of food everywhere in the world. So you measure the price of food everywhere, rich countries, poor countries, and take an average, and it's called the Food Price Index. And they started this in the year 2000 at 100, and then measured how the average food price has changed since the year 2000. And this is what they found. The food price increased very rapidly until 2009, when it was 220, which means that the average price of food throughout the world in the year 2009 was more than double the average price of food in the year 2000. Now that's due to lots of factors, of course, one of them the increasing population of the planet, but one of the factors is the fact that we've been having increasing amounts of extreme weather in this region affected by the jet stream. And this has been bringing on extreme heat and extreme cold, and that's causing a loss of crops. Now, that's an inconvenience for countries like Italy and Europe, but in poor countries, it's a disaster. If you look at poor countries in the Middle East, for instance, where you have most people or many people living in cities, very poor, not able to grow their own food because a city doesn't have any farmland, and having to buy food, but finding it increasingly difficult to buy food when the crop yield has gone down. So these little arrows and place names here are parts of the world where the price of food went very high, and the result was civil unrest, revolutions, warfare, because people didn't want to just starve, they would revolt. So places where revolts happened, it seems to correspond to times when the food price is very high. A whole collection of unrest here in 2009. Then the food price went down and then came up again in 2011, and again we had another collection of civil unrest. So this can only get worse. The population of the world is rising, and the climate is getting more and more uncertain because of the breakup of the jet stream. And the uncertain climate is producing high food prices, and therefore difficulty in buying food if you're living in a poor country. Now, the effect is going to be greatest in Africa. The UN did an analysis of what we can expect the population of different parts of the world to be by the end of this century. And we see most regions have an increase in population. Europe has a decrease, but most of the other regions of the world have an increase. But the increase is 20 to 30%, which is going to make it difficult to feed the world, certainly, but not impossible. But Africa, the prediction is the population will quadruple by the end of this century. And this is a truly frightening prospect, to have 4 times as many people in Africa. Because firstly, Africa can't feed itself now. It has to import food, especially food aid from the United States and Europe. Africa needs aid to provide enough food for people to eat. And now we're talking about 4 times as many people. So there'll be a massive effort by people to migrate out of Africa and come to Europe. We're already seeing that. But what looks like an increasing flow of migrants now is nothing compared to what will happen by the end of this century, when we'll have an increase from 1,100 million people to 4,380 million people. And we set an alarm, because how are we going to feed that many people? We can't feed this many people. So to feed 4 times as many people, it's really difficult to see how it can be done, unless Africa adopts contraception or adopts methods of reducing its population growth, which it isn't doing. And the result I can see is going to be a catastrophic disaster. So I'm afraid this is something that the statistics show the world is going to be suffering from. Let's look at other effects. All effects, I'm afraid, are bad. The next one is things happening to the ocean. Now, when you add more carbon dioxide to the atmosphere, some of that carbon dioxide dissolves in the ocean. And when you dissolve carbon dioxide in water, you get carbonic acid. Now, carbonic acid is an acid, so having an ocean with a higher level of carbon dioxide above it is going to mean that there's more dissolved carbon dioxide in the ocean, and the ocean will become more acidic. Now, the measurement of acidity is a function called pH, and the ocean pH has been going down, which means the acidity of the ocean has been going up, and this is measured in Hawaii. But if we look instead at acidity, here it is going up, and this is the ocean acidification has been going on since 1880, because ocean measurements have been done since then, and it's accelerated in recent years, since 1960, and this is because an acceleration in the amount of carbon dioxide in the atmosphere is giving you more acidity in the ocean. Now, that has a bad effect, because as the ocean gets more acidic, it means that creatures in the ocean that depend on low carbon dioxide levels die off. And one of that is shellfish, because shellfish of all kinds have shells which are made of calcium carbonate, that's chalk, and as the ocean gets more acidic, the acid dissolves the calcium carbonate. You know from school chemistry that when you add chalk to acid, the chalk dissolves and bubbles away. It's the shells of marine animals, everything from tiny animals right up to quite big shellfish. All of those shells are starting to dissolve because of the extra amount of carbon dioxide in the water as carbonate. So this acidity of the ocean has been rising. We see that it's rising in an accelerated way, and this is going to result in the loss of a lot of the marine life, because shellfish and also the little tiny shellfish called foraminifera, the minute shells, these normally sink to the seabed and we get rid of them. But if they dissolve back into the ocean, then that's adding to the amount of carbon dioxide in the water, and that again is increasing global warming. So we see an effect of killing off marine life and increasing global warming, both at the same time, because of the dissolving of carbon dioxide in the ocean. So another bad thing, everything that's happening as a result of global warming seems to be bad. There isn't any good thing. So that means we have to think, what can we do to try to offset all these bad things that are going on? Well, firstly, we want to offset the warming of the planet. Well, one way is to reduce carbon emissions, but the trouble is, if you reduce emissions, it doesn't actually cool the planet down. And the reason is that carbon dioxide stays in the atmosphere for a long time. One of the bad things about carbon dioxide emissions is that it stays, when you emit some from burning fossil fuels, it doesn't go away, it stays in the atmosphere for hundreds of years. So all the carbon dioxide that we have in the atmosphere now is carbon dioxide that some of it was put in the atmosphere 100 or 200 years ago by somebody burning coal, burning stock coal in a steamship in 1900. That carbon dioxide is still in the air today. So carbon dioxide you can't get rid of it by reducing your emissions. And this is a gigantic mistake which the world is making at the moment, and a lot of climate scientists are making that, is that they think that all we have to do is to reduce our carbon emissions, switch to away from fossil fuels, switch to electric batteries, do away with burning fossil fuels, and we'll be okay. But all that will happen is that the world will warm up more slowly from the remaining carbon emissions. It won't actually get cooler because there's less carbon dioxide in the atmosphere. There's always going to be more. So we need to do much more than just reduce our emissions. And unfortunately, the Intergovernmental Panel on Climate Change has only focused on reducing our emissions and not on removing carbon dioxide. So the only real solution is taking the carbon dioxide out of the atmosphere. So the Paris Agreement, by which everybody agreed to reduce their emissions, is false. It won't deliver a cooler climate. It will only deliver a warmer climate which is warming more slowly. We've got to get the temperature down, and the only way to do that is actually take carbon dioxide out of the atmosphere. And this is a process called direct air capture. And most scientists see that, but not all, and certainly politicians don't see it. So the politicians just talk about reducing our emissions. And you'll hear a lot about carbon emissions being reduced, but be suspicious, because it's not reducing emissions that cools the climate, it's taking carbon dioxide out of the atmosphere completely, and that's much more difficult. But I'll show some of the ways we can do it. Firstly, this is the danger. If we look at, this is the amount of different forms of energy that we use, and we can see that we're still using a lot of fossil fuels. The black, red and blue are coal, oil and gas, and we can see these are still the major sources of energy for the world. The small columns in the right are nuclear, wind and solar and hydropower. These are the ones we're trying to adopt to replace fossil fuels, wind and solar especially. But we haven't been very successful up to now, because you can see how fossil fuels still dominate. So we do have to reduce our emissions of carbon due to fossil fuel burning, but it's only a start. We need to do more than that. So this is the dilemma. This is what climate warming is going to be doing over time. If we don't do anything, the warming will accelerate. This is the red, and it's what scientists call business as usual. That's not doing anything but letting things go. If we cut our emissions aggressively, reduce our carbon dioxide that we emit, we can reduce the rate of warming of the climate, but we can't reduce it to below zero. We can't cool the climate. So the best we can do is reduce the warming rate to a lower rate of warming. We have to remove carbon dioxide, that's the green arrow, to actually bring the temperature down. There's another way, which I'll talk about, which is called radiation management, which can also help. But mainly it's taking carbon dioxide out of the atmosphere, can get us down in terms of cooling, while reducing our emissions can't. Now, the first way is this one called SRM, radiation management. And this is something that we can try and is being developed by a lot of groups, and I've been involved with some of that work, and it seems to me to be a great method. It's called marine cloud brightening. And what happens is that you want to release water vapor or water particles into clouds, and they then cause the clouds to become brighter. And a brighter cloud reflects more energy back into space, and that cools the climate. So here we see what water vapor does to clouds. It looks like it's looking like vapor trails from a plane looking down at the sea. This is the Bay of Biscay. In fact, you're looking up at the air, and this is where planes are flying overhead, and you're looking at, or actually ships are sailing down below, and you're looking at the water vapor produced by the ship's funnels. And here we see this pattern of water vapor. So the idea that was had by a Scottish scientist called Salter is that you build a ship. This is a kind of an unmanned ship, a drone ship, and you pump water up these masts with a very fine nozzle at the top to divide it up into very finely divided particles, and you release those into clouds, into low-lying clouds, especially the sort of clouds you get at sea, marine stratus clouds. The vessel is unmanned, but it's controlled by a computer, and the propulsion is these masts which actually revolve, and that gives you some propulsion. They're called Flettner rotors. So here's the design, and he reckons we need about 200 of these all over the world's oceans to produce enough vapor to cool, to brighten the clouds and increase the reflection of radiation from the Earth. So this describes what it is. We're increasing the droplet concentration in these low-lying clouds called stratocumulus, and the effect of making clouds brighter and therefore emit more radiation is called the Toomey effect, And that was only discovered in 1990, quite recent piece of basic physics. So you put these droplets into the cloud. So here we see the cloud with these droplets in, emitting radiation into space. And if you have the smaller the droplets you have, the higher the albedo. And therefore, that's the more radiation is sent out into space. And we know that because if you look at a thundercloud, it's dark. You know, when it's about to rain heavily, you see dark black clouds, whereas the clouds you see in fine weather are bright and fluffy. And that's because the bright clouds in fine weather have tiny water particles in them, which make the cloud bright, and it puts a lot of this brightness back out into space. The big dark clouds reflect less radiation into space, and that warms up the planet. So cooling the planet can be done by making clouds brighter. This is a wonderful thing which seems to work. So you can see this, how the size of the particles matters. If we look at glass beads ground up, here we have glass beads in this bottle ground up into 40 millimeter diameters, and it's quite dark. But if you grind it up further into 40 micron diameter, it becomes bright. So you imagine a cloud made up of these beads is going to be brighter and will reflect more radiation into space than a cloud made up of these big beads or big thunderclouds. So that's the Toomey effect. And so his design of Salter, we showed you before this design. He's come up with another design where you spray the water. Instead of spraying it vertically, you spray it horizontally. So just a new design. Well, that's one way, and that I think it would work. But let's look at what so far the world has only agreed on, which is the Paris Agreement of 2015. Now, the Paris Agreement says we need to try to keep warming to less than 2 degrees. That's because of the effect on crops, and even to try and keep it to 1.5 degrees. We should reduce our greenhouse gas emissions as quickly as we can. And each nation should say how fast it's going to go. Some nations haven't said that and aren't really doing very much, but every nation should be working together. But we see the weakness in the Paris Agreement is it only talks about emissions. It doesn't talk about carbon dioxide removal. And people are realizing this makes it a weak agreement. So let's look at the other ways, as well as marine cloud brightening, that we can get rid of carbon dioxide. Well, one way, these are 3 methods that have been proposed, and I don't think any of them are going to work except direct air capture. Firstly, afforestation means planting millions of trees. Now, trees are good. They take out carbon dioxide from the atmosphere and put in oxygen, but they're not that good. That is, if we consider the carbon dioxide put into the atmosphere in the whole of Europe and how many trees you'd have to plant to remove that, it turns out that the area of trees you'd have to plant in Europe is 6.4 million square kilometres. Now, the trouble is that is the area of Europe. So we'd have to cover the whole of Europe with trees in order to offset the carbon dioxide produced from our factories and cars. Well, obviously we can't do that. Another method is to burn crops collect up the carbon dioxide and store it. Well, that's not a great method either. That's going to use up 2.5 million square kilometres. And the final method that's been suggested is you take certain rocks, olivine rocks, that's limestone, you grind them up into powder, you spread them around the world, spread them on beaches and parks and roads, and they slowly absorb carbon dioxide. But it's very slow, and then when you've absorbed the carbon dioxide, you have to go and grind up some more rock. So it's not a great idea. So the only one that we think will work very well is air capture, where we take the carbon dioxide out of the atmosphere and let it put it somewhere. Well, one way to do this, but it's again not very powerful, is to produce a substance called biochar. And what that does is to take agricultural waste and to distill it in a kind of big boiler, and it produces a substance like charcoal and an oil, and it absorbs carbon dioxide. So it does take carbon dioxide out of the atmosphere. And the Amazon Indians used to produce biochar in order to be able to make their jungle less wet and better able to make food from it. This is some experiments in America where, in fact, biochar is being produced from the waste of pistachio nuts, which are being grown in an agricultural area of Ventura. And here, the digester, the plant that produces the biochar, is attached to the university's normal diesel generating plant to produce a decrease in the amount of carbon dioxide. So here it is, and here's one of the digesters. You have lots and lots of these that you drag through the fields, and you put pistachio nutshells into them, and you get this oil and biochar. So the nuts are actually, you're taking the carbon dioxide or taking the carbon out of these nutshells. So it seems stupid, but it works. And you need a lot of nuts, obviously, so you only do this in an agricultural district. That's the one solution. The biggest solution is actually take the carbon dioxide out of the atmosphere. And that's a huge job. And I don't know if we're going to be able to do it, but we put, at the moment, 42 gigatons of carbon dioxide into the atmosphere per year. That's gigantic, 42 billion tons. 1 gigaton is 1 billion tons. So if we want to cool the climate, we've got to take more carbon dioxide out than we put in. That means we have to take out more than 42 gigatons of carbon dioxide per year. How do we do that? Well, there are methods that have been put into effect, but on a small scale. One is a company in California where you take the carbon dioxide out of the air by absorbing it into a liquid which absorbs CO2, but then you react the carbon dioxide with lime, calcium oxide, to produce artificial limestone. And here is the artificial limestone being produced. And it's a way of doing something, here it is again, and this is a way of doing something with the carbon dioxide that you've taken out of the air. And so the way, here's the technician is showing us how the nodules of limestone that you've taken out of the air, you put into cement, and you produce a form of concrete in which you reduce the carbon dioxide content of the concrete by injecting it with this limestone. So this works, and in fact it's been demonstrated that the concrete that you produce from the carbon dioxide in the air is actually capable of doing all the jobs that normal concrete does, but you don't produce a lot of carbon dioxide from the manufacture of that concrete. And the demonstrator here was an airport terminal at San Francisco Airport, where they re-roofed the terminal with concrete made from carbon dioxide in the atmosphere, and there was a net reduction of carbon dioxide from the atmosphere by this process. That's an amazing thing, that we can reduce CO2, even if we use the CO2 to produce concrete, which is normally a method which actually adds more CO2. So there's a lot of promise in that method made by a company called Blue Planet. But there's also the simpler method of just pumping the carbon dioxide you've taken out of the air down underground. And the company that does that in Europe is called Clima, and its biggest plant is in Iceland. There's a plant to take carbon dioxide out of the air. You then pump the carbon dioxide down into big caverns underground, which exist because of the volcanic nature of Iceland. So the Icelandic volcanic cavities are the place you can put the CO2. The energy comes from the earth, from the warm production of the volcanoes. So this company is called Clima, and there was an experimental branch of this. The only one in Europe was run by Polytechnic of Turin, and it was situated in southern Italy, in Puglia. And so this is trying to do the same thing, take carbon dioxide out of the atmosphere and bury it, and using solar energy or wind energy to do it. So, and that again is in association with Climeworks. So the Polytechnic here in Turin is a leader in Europe in carbon dioxide removal, and it's unfortunately temporarily closed down that works because of COVID. So we can convert it into limestone. There's also ways you can convert it into jet fuel. Again, the trouble there is that when you've got the jet fuel, you burn it, and that produces carbon dioxide again. So we haven't really gained. This just shows the sequence of events where you blow air over a liquid which absorbs the carbon dioxide, and then you have to clean it, dry it, and pump it underground, or react it with something else to give you the limestone. So that's the principle. This is an experiment in Canada where you're blowing it over the absorber. That's all these blowers here, and turning it into jet fuel, which of course it doesn't use carbon. It doesn't use up any carbon dioxide, or doesn't produce any, but it's neutral. It doesn't get rid of any either. This is the plant in British Columbia. So here we have the methods that have been used, but only experimentally. what's needed, if this is going to remove 42 gigatons per year out of the atmosphere, then we can't just have a few experimental plants like this. We need a global effort, a gigantic global effort, to build thousands of these plants for removing CO2. And the question is, because the planet seems to be focusing on simply reducing emissions, which is a mistake, then we're never going to get the climate cooled down if we don't actually take CO2 out of the atmosphere. So that's what we have to be, the challenge that's facing the world, and the world isn't yet facing up to it. Anyway, I'll end up with a few, again, recent pictures. This is, again, the Greenland ice cap, which we went back to this year, and it was even darker than it was previous year. And this is where you see the black ice, which is because the amount of dirt has collected on the ice, and the ice itself has turned into water, so that what remains gets blacker and blacker, and that absorbs more and more radiation and gives us a more rapidly melting Greenland ice cap. So here the water's run off, but it hasn't run down to the bottom, it's collected in a kind of pool. That's this year. And just to show you something that's being done that I'm in touch with, and you may want, I'm part of it, and you may want to look at it as well. It's to encourage the use of electric cars instead of, the world shouldn't be, one way to reduce carbon emissions is to have electric cars which are driven by renewable energy, solar or wind energy, to generate the electricity which drives the car. So you have a battery. And of course the world is changing towards electric cars, but the method to try and encourage it was to have races using electric cars in remote places. So here's an electric car for a race on the Greenland ice cap. And in fact, this explains why I was on the Greenland ice cap. The company is called Extreme E, and you will be able to see the races if you go 5 times a year. They have races in remote places, and you can watch them. So this was the race that was done in Greenland last year. These are the drivers, and these are drivers helping the science by collecting ice and dirt samples from the ice cap. So the drivers were very helpful here, and this is one of the drivers you may recognise who has switched to racing electric cars. That's Jenson Button, who's a very famous Grand Prix driver, but he's now racing electric cars, and here he is posed in front of the Greenland ice cap. And this is another driver who, they have men and women drivers, and she's been a champion. And here we see where one of the other drivers pointing out where the water is melting off the ice cap and running down towards the sea. And here we see a sort of waterfall from the meltwater. So I'll just end with this rather frightening picture about, I talked about the threat to the climate due to cows. And in fact, this threat is much worse than people imagined. Most of the weight of biomass, that's the weight of people and things on this planet, is cows. Livestock make up 60% of the weight of mammals on planet Earth. Humans make up 36%, and wild animals, the ones you see about when you watch an Attenborough program, is only 4%. So nearly all or most of the weight of living creatures on this planet are cows, and cows produce methane. So we've got to try to reduce the amount of food, the amount of animal products that we eat, and try to eat more vegetable products if only, apart from cruelty, it's if only because that will reduce the number of cows and that will reduce the amount of methane they produce. And that will save the world, and it will save the wild animals as well that are dying out at a very rapid rate, like polar bears. And so I'll just show you some things you might want to look at. Obviously, Greta Thunberg has been raising the alarm, and everything she says is true. So the two things which I think you really would benefit from reading or seeing is this book describes all the things I've talked about today, and it's called Addio ai ghiacci, and I'm the author, and it's translated by my wife. And then a film, a full-length film produced by Leonardo DiCaprio, and it's all about these effects, including the methane, and the picture here shows a person who's been set on fire by putting his stick through a hole in sea ice into the methane-laden water. And it deals a lot with how we try to reduce carbon dioxide in the atmosphere, the thing I was talking about towards the end. So I recommend you try to see that film. You have to see a pirated version because they're not willing to, the producers don't like to show it. This is what will happen to us quickly if we're not careful. This is the Greenland ice sheet showing the thickness of the ice sheet on top of the continent. Now, Greenland is an island which has a kind of bowl shape, and in the middle it's below sea level. But because of the hugely thick ice sheet, 3,000 meters, Greenland is a mountain. It looks like a great bulging mountain. But if the ice sheet melts, all of that ice will go. That will raise sea level by about 7 meters, and we'll have a bowl in the middle. So those are some of the dire things that are happening. So what I'm saying really in all of this is that greenhouse warming is accelerating. It's not just warming the temperature, warming the air, it's changing sea level, it's changing it's affecting the presence of life in the ocean. It's increasing the amount of methane in the air. It's doing a lot of nasty things. It's producing these random extreme weather events. So we're not just getting a warming from our CO2, we're getting a lot of other bad effects on the planet. So we have got to reduce the CO2 from the atmosphere using the techniques I've talked about here. It's not good enough just to reduce emissions. We have to get rid of CO2. So I think we need high technology here and high engineering skill. So I'm sure that exists in Polito, and I look forward to you, some of you in the future, being involved in this work and helping to save the world from climate warming.